This is the Math Map Book Club, where ordinary parents encourage one another to develop an extraordinary appreciation of math. We love what we know and struggle over the unfamiliar. Through weekly conversation and exploration among friends, we can begin to enjoy ideas that seem difficult. Join our book club as we discover how math helps us to know God and to make Him known. This is Unfragmented, inspired by collage.
Hi, I'm Lee Bordens, and it's Wednesday, October 11th, 2023. Welcome to the Math Map Book Club, where Kirsty Gilpin and I discuss a math concept each week from our soon-to-be-released math curriculum for families with students in classical conversations communities. So welcome, everyone, and thanks for always dealing with technical difficulties with us. Kirsty, what do you got for us today?
Well, we are on lesson 23. We are in a new dimension, so it's a very exciting day. I always think so anyway. As we are counting down here, we only have a few lessons left, but this great picture here of the Milwaukee Art Museum, we chose for this lesson called Matrices. But I was just drawn today to the prayer by John Wycliffe. And he said, Lord Jesus, turn me toward you so that I may be completely yours. Heal me so that I may be completely whole. Without your grace and help, I can never be truly yours nor truly whole. And that just drew me in today as we're working so industriously to get the Math Map ready for its first printing. Just that reminder that we cannot do this on our own, that we rely on the Lord that is bringing all the pieces together. And so always just praying that He would be turning us towards Him first. So, but what else do you guys see? Either in that quote or in that piece of art?
So one thing that when you're talking about reading that prayer that I thought of with matrices and how it ties together with that prayer is that when we're doing math on our 2D piece of paper or trying to understand 3D and maybe 4 and ND, we're never completely whole because we're here in three-dimensional space. But a matrix allows us to see how it could go on and on and on, almost like it's a different analogy, but mirrors reflecting one another. That there's just so much more than we can even see in front of us. And so this picture reminds me of that. I also was wondering if anybody has been to see this actually at the Metropolitan in Milwaukee.
Maybe we need to take a field trip.
That's something we could do. We could do a tour of all the art in the Math Map. It would take a whole month to go see them all.
That would be amazing. Maybe that could be our celebratory tour when all 13 levels are published.
Hey. That just sounds like work to figure out where they are right now, but after we're not tired anymore, we can go. Any other observations by anybody?
Well, just the prayer says, turn me towards you. And this feels like we're being turned in some way. Kind of orienting ourselves to a certain perspective.
Yeah, I actually had to look this up because I can't really tell what I'm looking at. And maybe that's true. From our perspective, we don't see the whole.
Yeah, because you can tell the pictures cut off some of the windows that are up above.
Yeah, and then just even the way, like, what is that on the other side of the windows?
Venetian blinds.
Plantation blinds, yeah.
It looks like another building.
Yeah, because you're looking out from inside, I guess.
Yeah, you'll have to Google it. It's pretty interesting.
I think it's interesting in that same prayer where it says, without your grace and help, I can never be truly yours. And so it seems that not only are we giving ourselves to him, but without him receiving us, the transaction isn't complete. And so I really like that idea that it's to be completely his takes both him and us. I think I could think about that for a long time.
I like that you said transaction, because I think Paul speaks
I like
to
that, Jill, because we talk about that his grace, right? He freely offers his grace, but we have to receive it and accept it. All right. I am going to go ahead and move us to the next slide. Maybe.
It'll come.
The little blue circle of patience. All right. So this week, as we look at the math map, and we're making our way down the left-hand side, but we're still, I just want to point out, we're still just in that red column. That although we're talking sort of bigger ideas, where everything that we've been looking at, the lesson pages that we've been looking at are really, they're all in this column here. And so there's all these other numbers and domains that we have yet left to explore these same topics with. And so it's easy sometimes to think, oh, I've got to do it all. But just that reminder that, right, this is meant to be done repetitively over many years as we look at those ideas. So the question that I had for us this week, when we think about mathematics and the idea that we're going into this fourth dimension here, which is a very abstract idea, right? How do we use patterns to communicate abstract ideas?
So I know Crystal has a question that might help lead there. She was going to ask us about something in 0D, and maybe we can look at that and then go to 1D, 2D, 3D, 4D and see what some of those patterns are. So Crystal, what was your question?
So we see Euclid's definition in the math map. A point is that which has no part, but we realized recently that we're used to thinking of zero or a point as an exact location. But it seems like that definition actually requires a 2D mind frame. Like, I don't know, am I thinking correctly? Like, how can you explain an exact location without 2 dimensions?
Well, it requires at least 1 dimension, right? So I could have a location, if I'm in 1D, then I can have a location on my coordinate axis or my number line. Once I'm in 2D, I can define a location that's in the plane. If I was in 3D, I can define a location that's in space. In 4D, it would be a location in hyperspace. But you're right, in 0D, it can't be a location. And so that tendency for us to use the idea of location, because when I think about location and intersections, it makes it easier for me to go, yes, that point really exists. Even though it doesn't have any dimension, I know that it exists because it has to exist here in my 3D world. But in 0D, there is 1 location, and that point is it, right? It can't define a different location. There's only 1 place in 0D, and that's that point. There's nothing outside of that point. And that's where we go back to Euclid. So location is more of an algebraic understanding of point, because we're assigning coordinates, where going back to Euclid's definition of that which has no part, or a point is that which has no length, no width, no height, right? No dimension. That gives us that geometric understanding of something that exists, but it has no measurement.
I mean, really, Crystal, if I'm understanding your question right, we live in 3D space. We can't get rid of that. And just to even think apparently requires 3 dimensions because it's contained in being human. And yet, what space are my thoughts taking up? Like, where are they? So, so it's kind of freaky like that. So if you go from 2D to 1D, you're losing your one of the dimensions. But when we go from 1D to 0D and we're losing the line, we aren't losing the numbers. They're still there, but there's no where to where they are. The 1D gives us the where. So they're like more like thoughts in that sense.
And isn't location always relative to other things? And if there's nothing else to compare it to, and it isn't anywhere. I mean,
That
it's,
is- yep.
So because numbers are abstract and the numerals are what's concrete. So numbers, like use this idea of 3-ness in the curriculum or 4-ness or 5-ness, that no matter where I am in the universe, the idea of 3 is going to be the same, but it will not be represented the same way. And so it's just interesting to think about where thoughts are located, and numbers are thoughts. Probably didn't help you, Crystal.
It gave me a lot to think about, Lee.
I was just thinking when we were talking about that and the idea of location being relative, right? If we talk about where we live, right? I can give you my address and tell you where I live, and it's going to tell you my house number, which differentiates me from other places on my street, which differentiates me from other places in my my town or wherever it is that I live, my unincorporated area of a county, that differentiates me from the rest of the state, which differentiates me from a country, which differentiates me perhaps from the continent, right? And then I could say, well, I'm on the earth, which differentiates me from other planets in our solar system, that differentiates me from other star systems, in the Milky Way, right? So now I've differentiated myself within the galaxy, but now I'm saying where I live in the galaxy. And once I name that galaxy the Milky Way, that differentiates me from other places in the universe. But that's it. That's as wide as I can go, right? I can't say, well, I'm in this universe, because there's only one. So that's kind of how it is for a point, right? Only going the other direction, right? The point, there is nowhere else. That just is, right? I'm in the universe. The point is the point. I don't know if that analogy helps any.
I think what I'm taking away is a summary of what Lee and you said, which is we are used to thinking in 3D. So when we've been working our way backwards and kind of looking at things from the context of 3D. So location has 3D context or 2D context, and then even a longitude line seems to have, we were talking about this with some people, a dimension or more a 2D context, but the math map is kind of teaching us to go the other way, to start with nothingness, because that's what God did. And I don't know, I'm not articulating that well, but in my head it makes sense.
Well, that's when you're dialectic but not rhetorical. So that helps us to figure out where to go next, but I understood what you said. I'm just curious, Jill said that she talked about what space are my thoughts taking up with her seminar. What did they say?
Well, we had students who believed that they don't take up space, and they were quick to answer, nope, no space. They don't take up any space. And others were saying, well, yes, because I think some of their parents had listened to some YouTube videos about how our thoughts can be tracked in the brain, maybe different things, that they're like, oh, there's these receptors, or I'm not sure the words because I didn't watch the video, but the different things that like maybe synapses or words, lots of words that I new grammar. And so they were saying, no, it does. It creates pathways in the brain, and those pathways take up space. So it was very interesting to hear that it wasn't it was brief, but they had big ideas. Just like we also asked, somebody said, is a line a shape? And so then I said, well, what do you think? And they started talking about that too. Well, if it's thick, anyway, it's great that I can take some of the questions we use in math club and just pose them and see what they do with them. And they have thoughts. They're excited to consider those things. But we didn't arrive at a conclusion.
That's good conversation. So Kirsty, lead us to where, was there an answer you wanted us to talk about or from this question?
Well, no, it's really what we just did was looking at patterns, right? And so Crystal, as you said, we can either start broad and take away and see the pattern, right, of taking things away, or we can start small and add to and see the patterns. But it's those patterns that are going to help us. Right, we are familiar with 3D, that we are, I know, I'm sorry. That we are familiar with this, right? This is everything we see. And so when we want to understand 2D, 1D, 0D, we're always looking for that pattern, right? Well, what did it look like in 3D? What would it look like if that part was gone? Right, or going the other way. And so it's just remembering, sort of like we use analogies, right? They're a specific pattern. Patterns in math may be more than just right, comparing two ideas. They're looking at these patterns that continue on that are going to help us as we look at the fourth dimension and beyond. So,
you know, we can use the patterns too to be analogous. So like in our analogies course that we have in Challenge, you could have make up a problem that said something like a human space is to intersecting spaces as, and then or even say like 3D is to 4D as volume is to, and then finish it.
they don't know that answer yet. But let's look at our next slide. So we are here. This is what we're going to be talking about today, is lesson 23, which is titled Matrices. But notice I also circled 4D, harmonics, intersected spaces. I'll talk about that just briefly because there's one of our patterns. If I have my point and then I have my line, right? I can look at relationships now between points. If I then have two lines that intersect, those intersecting lines are going to define a plane. And if those planes, I have two different planes that intersect, they're going to define our 3D human space. So now, as we move into 4D, think about if we have two infinite 3D spaces, right? And so this is where a lot of times our thinking just collapses and we start using images like cubes to represent those infinite spaces. But we have to really hold on to that idea that they are infinite. So I have two infinite separate spaces that intersect in some way, right? That's a picture of what 4D would look like.
If we could picture.
Right, so it's really hard to picture because it's hard enough to picture an infinite 3D space, and now picture that there's another one that isn't the same one and somehow intersects that one. And that's where we are going with 4D. That's why it's called intersected spaces. So here is our looking at our 4D and our chart. So this is just a couple of pieces from the first chart for this lesson. And notice at the top, we are defining the fourth dimension, and we're representing it by a shape called a tesseract. But quick question for you, is that a finite or infinite shape, the way that it's drawn?
Finite, the way it's drawn.
Right. So we
Drawn
draw
finite.
Yeah, it looks very finite, but we have to think about the fact that those are really trying to give you that image of two infinite spaces that are intersecting. So
One of the reasons we have a shape for 4D and for ND was so that as you went down the chevron on the left to look at the map, there was something, another like a visual peg to hang the kids' hats on to remind them, oh yeah, this is where I am. It's not the right shape because we can't draw it, but it helps me remember that that's where I'm thinking.
So we've defined it and we say it's that which has infinite length, width, and height, and we're adding a new dimension called breadth. And we just realized that we have that this needed an edit. So it's actually defined by 5 points, not in the same space. And then Lee was just asking about volume. And so here's the answer to her analogy, right? 3D is to 4D. As volume is to capacity. So volume was our measure of something in 3D, and capacity is our measure of something that's in 4D. So
it says content. It doesn't say capacity, Kirsty. So I'll go
yes,
double check it.
that's a really good good thing.
I'm
that
pretty sure. Yeah, so we'll all go double check, but I would argue that content was the word and not capacity.
Okay.
So we'll see which one it is.
So let's start off just by, before we talk about what you think you know about what's 4D, what are some things you know about what 0, 1, 2, and 3D? And we've talked a little bit about this, but what are some other things that you might know about those dimensions?
One, 2, and 3D are all infinite, but in the limit of their directions.
Okay. And you can know things individually about the dimensions, and you can look at what's on the screen.
Just something that's familiar is that 1D measures length and 2D measures length and width and 3D measures length, width, and height. And I feel like at the very beginning of the math map, when I didn't know anything at all, then I knew that. So I remembered that from school. And so I feel that's like the most familiar.
But that's really good, Babs, right? That's not a minor thing. Those are the names of those dimensions, or the right of each of those dimensions. That's really great. What else do we know?
So this is kind of a popular cultural connection, but when I see hyperspace, like I'm thinking like when you're in a spaceship and you go and you then you're in a different space.
It just turns out mathematicians use the same word as the science fiction writers.
I think they steal it from the math people.
Oh, and something else I was going to tell you, when you were talking about how it's hard to picture like 4D stuff, for some reason I always think about Avengers, because they always have this, it's like the imaginary screen that they touch and stuff appears. And I always feel like that is like what 4D's like, because they can turn things around and they're like, it's like hanging there, but it's not really real, like you can't touch all those pieces. But so whoever's making that, I feel like they know what 4D could be, or ND, or all the other, so that's what I picture when I hear things like 4D.
So Lee, I just did a quick look, and I think capacity is the general word. So length would be a capacity in 1D.
I think so.
Area is the capacity in 2D, volume is the capacity in 3D, and content is a capacity in 4D. So
what would you guys think if instead of saying measure, it said capacity on that chart?
Well, what I was thinking when I saw measure was that there are other measurements within, like 3D, you can have a surface area. That is a way of measuring 3D that is not volume.
Mhm.
I don't know if that's helpful, but
I like both words. I feel like each word
you
has,
can't have both, Jill.
Give on.
I don't like when people tell me no.
I like capacity because when I think of measure, I'm thinking that maybe what would be there would be like centimeters or inches or like what you measure in. So I think maybe capacity would be better in that space.
What were you saying though, that capacity is kind of like a genus and content is the species? I mean, like,
Yeah.
Yes.
yeah,
Is
my instinct is
measure is so
capacity.
broad.
Yeah.
Go ahead, Carrie.
I was gonna say, my instinct, I think, is capacity, because I measure seems broader to me than capacity. I think capacity is a specific kind of measure. But I don't know my terms well enough to be sure.
Apparently we don't either.
But
So
I did
here's-
notice in the top slide, it says the fourth power of anything, 8 to the 4 can represent a capacity, but then measure we have content. So it might help for those to match whatever is decided.
Yeah.
We'll fix it. Thank you for catching that.
Yeah. When we see things broken up, right, it's a new perspective, just like the picture of the museum, right? Depending on how you look at it, you have a different perspective. And so a lot of these charts, some of this content was written 5 years ago and you just kind of glom over it. And then when you break it up and you see it differently, you go, oh, wait,
We missed that one.
you missed that. So
explain the 5 points. I thought we did earlier today with me was really good, starting at 3-dimensional space.
sure. So how many points are there in 0D?
one.
One, right? 1 point. And then if I have another point, right, what does that define? Like, what do we know about 2 points defining something? What do they have to be
On a line.
on a line, right? If I have 2 points, they have to be on the same line. It doesn't matter where I move those points, the 2 points have to be on the same line. If I have a third point, it doesn't matter where that line was that these two created. If I have a third point, all 3 points have to lie in the same what?
Line.
Plane, right? And so if you haven't heard it before, right, that's why stools are inherently more stable, right? A 3-legged stool will never wobble like a 4-legged stool or a 4-legged table will, because those 3 points are always going to be in the same plane. As soon as I have a fourth point, it may or may not lie in that same plane. And so what happens if you have a table that wobbles and it's got 4 legs is that that I have these 3 points are in the same plane and these 3 points are in the same plane, but because they're not always in the same plane, my table wobbles back and forth between planes. Right? But those 4 points, even though they're not in the same plane, do have to be in the same space. Right? So now I have 4 points and they're in the same space. If I take another point that's not in that space, right, I need another dimension, right? That would be our 4th dimension. And so that's why it's 5 points that are not all in the same space or not co-spacer.
We made that word up
So-
today.
Can I clarify a distinction that
Yeah.
to make sure I'm understanding?
Yes.
So the dimensional space is defined by 1 through like 0 to B is 0D space, if you can call it that, has 1
Yeah.
point, and then 2D space, etc. But points within the space, so like like you cannot define the location in 0D. But when you're naming a point in 1D, that requires 1 point. So there's,
Yes.
I'm
One
not, I
coordinate.
mean,
Yes.
so
one
coordinates, so coordinates. Okay,
So coordinates match the dimension number, but the
Right.
number of points to define it are one more.
Or
Right.
so that's a pattern that you can look at, like you were saying, what are some, how can you imagine the next dimension? So we just have to picture this fifth point that is not in the same space.
well, and I'm thinking like what immediately came to mind is like, I wanted to name that point the origin. But I don't know that that's quite right.
The
Okay.
fifth point you wanted to
The
name the
fifth
origin?
point, yep,
Yeah, the point is that the point.
I know.
The fifth
The point is,
hard.
but everything
thing
came
is,
from nothing,
yes,
so it's like that, I don't know.
Because there are 5 points in 4D space. There's infinite number of points in 4D space, but we're
That's
trying to
true.
say to get to that next dimension, you got to throw the point outside of where you are.
Yeah.
Okay, gotcha. Bye. Thank you.
So I've gone back to the chart for 19, and in it, that same little box that says the third dimension, space is defined by 4 non-coplanar points. So you would be
Right.
just following that pattern, and it's just a different pattern. So as far as how many points define it, you're adding one to what the dimension is. But as far as how many points that you use for an address within it, you're using the same number of points,
The dimension, yeah.
which it can be confusing.
Yes.
But I think also for me, I'm able to go back to the pattern, and the students will be able to go back to the pattern of, okay, what did it say when we were introduced to 3D? What did it say when we were introduced to 2D? What did it say when we were introduced to 1D? So we can match that box, from all the different dimensions.
Yes.
I
And so
really like that you said to get to another dimension, move up to another dimension, you have to throw a point outside of where you are. I think that could be like if you were doing a math field day, that activity of throwing a piece of paper out, I think that could be super cool and a hands-on neat thing.
Yeah. It's just hard because we're 3D throwing 3D things, but if they can kind of imagine maybe an ant down in the earth with no dimension, throws out, he spits and whoop, now it's in 3D.
But I think what we just hit on though is the power that pattern has, right? That I'm just making this note so I don't forget about it. That the power that pattern has, that I don't really have to, right? I can think these things are true about 4D because I've seen them to be true in 0, 1, 2, and 3D. Right. So if there was no coordinates in 0D and 1 coordinate in 1D and 2 coordinates in 2D and 3 coordinates in 3D, and so how many coordinates do I think there are going to be in 4D? 4, right? And there's 1 named dimension in 1D and 2 named dimension in 2D and 3 named dimensions in 3D. How many named dimensions do I expect there's going to be in 4D? 4, right? And there's a measure of capacity in 1D, right? I can measure the 1D space. I can measure 2D space. I can measure 3D space. Do I expect to be able to measure 4D space?
In my imagination.
In our imagination, right? That there is some measure. We don't know what it is, right? But we look at it and we go, well, if I could take some chunk of 3D and measure it, I guess I could take some chunk of 4D and measure it, right? Not the capability to do that, right? But the theoretical possibility of doing that.
Okay.
If I can define my position in 1D and in 2D and in 3D, do I expect I could probably come up with a way to define my position in 4D? Right. And so this is this beautiful thing where I can take these patterns that I can see, these concrete patterns, and I can say, now I can think about this thing that I can't see, and I can imagine it by creating this abstraction, right? This prediction of what's going to be there, right? Is it possible that 4D doesn't follow any of the rules and everything's different?
Maybe,
Maybe.
we don't know. But that's why we guess, or, we keep the pattern. What's that word? Extrapolate?
Yes.
Which is always a dangerous logical tool.
So
This reminds me of, I won't say who, but I was at a Christian college attending a philosophy course by a very famous philosopher. I got invited to it, and he was using Santa Claus as his example for the imaginary versus the real. And I told him, but Santa Claus is real. And he looked at me and said, you don't really believe that, do you? I said, oh, you don't know how big my imagination is. So what I think happens is you get to know math, and as a Christian, we live in a world with windows. We can see outside, and people who aren't Christians and don't have an imagination, they're stuck in this material space.
all right, well, we are getting close on time, so this has been a great conversation, but I'm going to move us along. I briefly just remind you that we are going to be rolling out the curriculum over the next few years. And although I haven't put it on here, I just thought I would mention, because I know a lot of our CC leaders are on this call, SRs and so forth. And we're really excited because one of the reasons, Lee had a lot of reasons that she can talk about for why she wanted to have a CC math curriculum. But I know one of the reasons was that she wanted to be able to support tutors and families in mathematics. And when you're using somebody else's materials, that's hard to do because you're not allowed to create derivative works. You're not allowed to create extra things to go alongside of that. But with the math map, we can fully support our tutors and our families. And so there's going to be a lot of things that we're going to be doing over the course of the next several months for our incoming Challenge A tutors, as well as for families, things like this book club that we're doing. So I just want to say, watch out for all of that, because I think it's really great, the work that CC is putting into supporting the families and the tutors, especially as we roll out the math map.
Thanks.
All right, so not a lot of time for these questions. I'm going to skip the first one because I think we'd like to get down to the last one. I am going to point out to you that if you've noticed in some past weeks, I'm going to change my thing to a highlighter here and see if it'll work. That this top section here used to go all the way across, and this is where we would have graphs in the top section of each page. Now that we're in the fourth dimension, I just want to point out here that this sidebar here, now it decides to work, that this sidebar here is where that sort of patterning is going to go. So every lesson in 4D is going to have graphs that go down the side like this for students to see. So if you've been paying attention to that, I just wanted to point that out to everybody. So okay, I'll get rid of that, and let's go ahead and talk about this sidebar. And if you notice, it says it has all of our dimensions from 0D to 4D, and then at the top it says none because we're just tracing, and then it says W and E, and then W and E and S and S and N and S. What are those letters representing, do you think?
Directions.
Directions. Yeah. All right. So there's no directions in 0D. How many directions are there in 1D?
2.
Right. Does that make sense? Right? Because if I'm infinite, I can go both ways. So how many dimensions are there in 2D?
Oh, that looks like 4.
Mhm.
4 directions?
4 directions, right? So each dimension has a direction. So how many directions are there in 3D?
6.
6. So how many directions are there going to be in 4D?
8.
How many in 5D?
10?
10.
10 and 6D?
12.
Got it.
And what gets hard is naming them.
Grammar.
It is. I mean, even just look at 2D and 3D, right? Because could we have, instead of west and east, could we have done left and right and up and down?
Right.
Yeah,
So does up
you
and
could do
down,
Anna and Kata.
right? Is that 2D or is that 3D, right? So these words are challenging because of how we use them, that we really always need to be very specific about what we're doing, right? What do we mean? What dimension are we in? And then as Donna pointed out, right, we've got these new words. They may be very unfamiliar to people. This idea of Anna and Kata, which if you look them up, it's an up towards and a down away from. Okay. So now when we're in the 4th dimension, we've got weird words that are describing strange directions, right? That we may not even really know what that means. So if we went to 5D, what could we call those directions?
Yin and yang, Tom and Jerry.
So let's go ahead and jump down to our last question here, and look at that box on the left there. Why do you think, if you have any ideas, why do you think we chose to call this lesson matrices?
Because of the tesseract and spaces within spaces, and
Because we really need a way to be able to define all of those different spaces, don't we? A nice, easy way to define all of those spaces. And a matrix is one way that we can do that. And so a matrix is just this array. So if you look in the middle there where it says 4, 5, 1 and 3, 2, 7, but they're in rows and columns. We have 2 rows and 3 columns, and then they have that sort of box around them. That's a matrix. That's all a matrix is an arrangement, sort of in rows and columns that way.
So that relates then to our 5 canons of rhetoric, because arrangement's one of those canons. How do you represent the data?
And so then you made it plural, because if you have one matrix and you put another matrix intersecting with it, now you're in a different dimension.
Well, that's interesting. Well, I just have more than one matrix. I have matrices. So we look at more than one, but actually a lot of that dimensional intersection happens within a matrix. So each row can represent, in this case, I have 3 numbers there. They could represent 2 different planes. Each of those 3 numbers could represent a plane. So there's the plane that would be 4x plus 5x plus z, and there could be a plane that's 3x plus 2y plus 7z. And so now I can actually take 2 planes, 2 spaces, and look at them in one matrix. So there's a lot of different ways. We're not going to get into all of that because that's a 13-year journey.
The thing is that's so cool is that you can actually do very simply 4th dimension and higher calculations using matrices. So you can't see what you're doing, but you could do a 6 by 6 dimensional calculation if you learn how to use matrices.
Matrices look less intimidating because they're just numbers. But they represent, I'm just gonna write this in here, right? That it doesn't want to write for me. All right, there we go. 4x plus 5y plus 1z equals 0, right? That would be, that's what it represents. But isn't it nice that we can just deal with the numbers and we can toss those letters out? Right, I don't need to worry about those in this case. I can do things that are just those numbers. So when we look at it from that perspective, it's really approachable from an arithmetic perspective, right? So even our youngest students could add and subtract within a matrix. They could multiply within a matrix. But our older students, right, can take these ideas about matrices and start looking at, well, what does this tell us about these different dimensions? Right? And how can
connect it to the algebra.
and connect it to the algebra, yeah.
Which we're not gonna do today. So
No.
Kirsty, we're out of time. You guys are really great because you ask a lot of questions and make it really interesting for me. I'm so happy to be here each week. And I look forward to seeing you all next week where we will look at week 24. Rates, word problems. Thanks, bye.